Yifei, maybe it's better to make a full screen so it's larger.
Oh. Let me try.
You press, yeah, perfect.
Okay.
Okay. Okay, shall we start?
Okay.
All right, so next speaker is Yifei Chen from Beijing. He will tell us about singularities and toric fibrations. Please.
Thank you very much for the introduction, and also thank you very much for organizers to give me such a chance. Very interesting activities. All right, so this is a joint work with Kosher Yerka, and I think it is a good chance to dedicate our advisors, Professor Shokurov. This year is his 70th birthday. So Vanya and Jihong and myself, also Kosher Yerka. Oh, okay, so today I'm going to talk about something about singularities. So singularities play an important role in minimal model program. So we know in minimal model program, the extremal contractions are very basic operations. So for example, there are basically three types. One is called divisorial contraction. The other is flipping contraction. The third one is called Mori fiber space. So the first two are birational, and in the first two cases, the singularities of Z and singularities of X plus is as good as the singularities of X. If this is the third case, for the Mori fiber space case, F is not birational. In this case, dimension Z is less than dimension of X. So in this case, the singularities can be worse, but the conjecture says it can be worse, but cannot be arbitrarily worse. It should be under control. So the first conjecture is due to McKernan. So he conjectured, suppose D is a natural number, denotes dimension, and epsilon is a positive real number. Then there would exist some delta depending only on D and epsilon, satisfy the following. So if X is an epsilon LC, dimension D and Q factorial, F is a Mori fiber space, then the singularity of Z is delta epsilon. So this delta can be smaller than epsilon, but it is controlled. It is function of D and epsilon. So known cases, if dimension D is less or equal to 2, there is nothing to prove, because in this case, X is a surface and Z is either a point or a normal curve. But for a normal curve, it is automatically smooth. So for D less or equal to 2 is trivial. And in 2008, Mori and Prokhorov, they proved for D equals 3 and epsilon is 1, which means axis has terminal singularities. In this case, they can prove we can take delta equals 1. And in 2014, Alexeyev and Borisov, they proved for toric morphisms of toric varieties, the conjecture holds. So we will mention this case later because we need use some of them, their method. The other more general conjecture is due to Shokurov, and we will introduce it before. We will introduce a canonical bundle formula first. So suppose we have a KLT trivial fibration from X to Z. So KLT trivial means we have a pair. Kx plus B is trivial over Z. Which means Kx plus B is a pullback of some R Cartier divisors from Z, and XB is a KLT pair. Then we have a decomposition. Kx plus B. Oh, sorry, here I missed something. So here should be F pullback of this. And BZ is defined as P P runs from all prime divisor over Z, and AP is called log canonical threshold and also mentioned, I think, in Kerway's talk. XB and F pullback of D. D takes D should be DP. DP is the generic point of P because P is running through all Wei divisors of this Z. So after this BZ is defined, MZ just subtraction. And BZ and MZ satisfy some functorial property, some base chain, not base chain, some diagram. For example, if you have a Z prime to Z is a birational morphism, and you would have a diagram, and then you can define BZ prime, MZ prime, they should satisfy some functorial property. So this is called Kawamata canonical bundle formula. And this is very powerful formula to study like Mori fiber space or like the fiber are Calabi-Yau type, like elliptic fibration. So then we can introduce Shokurov's conjecture and stated in the language of generalized pair. So similarly, we have D denotes dimension, epsilon is a real number. Then there exists a real number delta greater than 0, satisfy the following. So XB is a epsilon LC pair, and this is a trivial, KX plus B is a trivial. However, in this case, we only consider X is of Fano type over Z. We do not consider fibers Calabi-Yau type. The conjecture is this Z, BZ plus MZ is generalized delta LC. So if you are not familiar with this language, that's okay. So basically it means for any discriminant divisors BZ prime, Z prime is a birational model of Z. They all have coefficients less or equal to 1 minus delta. Okay. And in particular, this conjecture would imply the multiplicities of fibers of F over codimension 1 points are bounded in terms of D and epsilon. So imagine we have a log smooth pair, XP or XB. If B is a multiple fiber, say Xn times B, then log canonical threshold of this XnB is 1 over n. So if this singularity is bounded, then this multiplicity of this fiber cannot be arbitrarily large. Otherwise, this coefficient will be very small. So this is basically this phenomenon. And this phenomenon was studied by Mori and Pencroft in 2009. And they showed if X to Z is a terminal threefold of the Del Pezzo fibration onto a smooth curve, then the multiplicities of fibers are bounded by 6. And actually, they, I think, as I remember, like they seems classified all possibilities of this. All right, so the known results for Shokurov's conjecture due to Birka in two of his papers combined. One is from 2004, the other is his famous paper about BAB conjecture. So the result says Shokurov's conjecture holds if F is a general fiber and support of B restrict to F is log bounded. Well, here is a typo. Well, F is a general fiber of small f, this morphism. And the conjecture, in particular, the conjecture holds if the coefficients of all horizontal components of B are greater or equal to tau. So in the latter case, in his BAB conjecture paper, he proved this part is log bounded. And this part is, first part is proved in his 2014 paper. This is known for Shokurov's conjecture. So today, we try to study for Toric case. Precisely, if D is a natural number and epsilon is a positive real number, then there exist alpha and delta for positive real numbers, depending only on D and epsilon. Satisfy the following. Assume X and delta is a projective toric pair of dimension D, where X is a toric invariant divisors, which means X, this delta just X minus this torus. C, if we're working over, in this paper, we're working over the field of complex numbers. So minus C star D, that's the toric invariant divisor. And we consider a toric contraction X to Z. So an XB is an epsilon LC pair and B is a Q Cartier, but B is not necessarily toric, which means B, the support of B can be outside of this delta. And I'll assume moreover KX plus B is trivial over Z. What we can prove is this Z, gamma alpha Z plus N alpha Z is generalized delta LC. So what is this? Alpha is there exists some alpha, but we cannot prove yet for alpha is 1. We have to do something like we call average. Average, so alpha is a positive real number between 0 and 1. We can take such a divisor. And then we can, for this divisor, we have this canonical bounded formula. What we can prove is for this pair, Z, this pair is generalized delta LC. So in other words, we cannot prove Shokurov's conjecture so far, because Shokurov's conjecture XB directly BZ plus MZ. It can only prove there exists some alpha, and such that this pair is generalized delta LC. Okay. But with this result, we have some pleasant corollaries. One, the first one is if we consider a Torri-Fano contraction X to Z, and X is epsilon LC, then the multiplicities of fibers are bounded by some M. M only depend on D and epsilon. This is one corollary. The other corollary is we can reprove their result with another method, Alexeyev and Borisov. So basically, they proved for McKernan's conjecture for toric varieties and toric morphism case. So these are two corollaries. Okay. All right. So let me explain the proof. Actually, I want to say our joint work starting from this example, and we've realized actually this example can be generalized. So first, we consider special case of before. Original motivation is try to prove the multiplicity of fibers are bounded. So a special case says this. So let D be an integer or natural number, and epsilon is a positive real number. We assume X is a toric variety of dimension D with epsilon LC singularities. And we assume for a special case, X to Z, Z is just A1, is a toric Mori fiber space. A1 is a fine line. So in this case, the special fiber just the pullback of this zero. Zero is the origin of A1. And we want to show the multiplicity of G is bounded by some natural number L, but this L depending only on D and epsilon. So this is the original case we want to work. And I will explain the proof of this, and then the proof of general theorem is similar to this case. Okay. All right. So I have to use some toric geometry. So we know that a toric variety can be defined by lattice and fan. So I think the gist of toric geometry just explain every geometric properties of toric varieties in terms of lattice fan. And lattice fan, they have many combinatoric properties. So first, we need to describe what is the lattice and fan description of toric Mori fiber space. But this is not new at all. This is already found in Alexeyev and Borisov's paper when they prove the McKernan's conjecture for toric varieties. And actually, they actually for F from X to Z, but here we only interested X to A1, so we can be more precise. So suppose F is X to A1 is a toric Mori fibration, and X is Q factorial of dimension D. We know that X is given by some lattice NX, I denoted by Z to D, and A1 is given by this lattice Z. And this lattice, the morphism of lattice, I have to excuse, F here denotes the morphism of lattice, not the general fiber before. So this is a morphism. And we can extend this morphism to the linear map, this R linear map, just by tensoring R from RD to R. Then we have the following. First, we can choose the basis of NX tensor R, which is R to D, such that FD is just projection of R to D to the last coordinates. So first, we just do a projection onto only the last coordinate left. And here it says for X, it has exactly D plus 1 one-dimensional cones, Ri, I from 1 to D plus 1. And when R1 to RD are in kernel F, this can be read from this. So and RD plus 1 is mapped onto the ray of C. The ray of C. What is ray of C? Just this this NA1 tensor R. I will show you later by a picture. Maybe this is more clear. So this D plus 1, how to compute this? This is because toric Mori fiber space relative Picard number 1. But for Picard number for toric variety, it actually can be computed by the number of rays of this variety minus the number of rays of this variety minus relative dimension equals 1. Then we can get the number of one-dimensional rays here is D plus 1. This is a special for toric varieties. Okay. And also we know all the cones, what's the shape of all the cones, just some combinatoric here. Another point we also need to use, a general fiber F of F is multiplicity 1, toric final variety of Picard number 1, possibly singular. So from the number of rays and also the computation of Picard number of toric varieties, we can get this. The general fiber is a Picard number 1 toric variety, but possibly singular. For example, weighted projective spaces. And the other thing we also need this fact is, if we minus the origin, this F inverse U is nothing a product F times U. This is a structure of this toric Mori fiber space. The last one, this is not contained in the Alexeyev and Borisov's paper, but it's not difficult to get. This information actually describe the multiplicities of central fiber. So suppose Vd plus 1 is the primitive element of the ray Rd plus 1. This ray mapped onto the one-dimensional maps to A1. And this shows the D's coordinates of this Vd plus 1 is the multiplicity of G. So actually this can be read from the D's coordinates of this vector, which is the multiplicity. So this is all we need for description of toric Mori fiber space. Okay. We also need to mention if we need to prove for Mori fiber space of relative dimension 1, actually already proved by Bierka in 2014. He already proved this, but I still want to introduce this toric surface case because it can give us some examples and also to understand this lattice and band description. So I want to include this part. So even Bierka already proved this. So suppose X is dimension 2 is a toric surface. This is relative Picard number 1 toric Mori fiber space. It is by Bierka's result is already proved, but I want to use the lattice and fan description to prove it again. And in this case, we can get some explicit bound for this multiplicity L. So this case is F from X to A1 is a toric Mori fiber space. X is a toric surface. The first thing is the general fiber of F is P1. Also, the support of the special fiber is also P1. So before we said the general fiber is a Picard number 1 toric variety, possibly singular, but for curve case, because it is normal, so it has to be smooth, so it's just P1. And if X has terminal singularity, in surface case, X is smooth, then there is no multiple fibers, which means we can take L just 1. In this case, if X is a smooth surface and all fibers are P1, then there exists some section. So if there exists some section over some smooth surface, then we know there are no multiple fibers. So this case is easy to see. If X has canonical singularity or equivalently epsilon is 1, then we can take L is 2. The multiplicity is up to 2. And we will skip the proof of this and we will see the third proof. We will prove the third. If X is of epsilon LC, then we can take L to be 8 over epsilon square. So this is an effective bound for the multiplicity. Actually, this bound may not be sharp, but it is some effective bound. I think in this case, it is sharp, canonical singularities. So let me explain a little bit for this surface case to illustrate the idea. Okay, so by the, let me recall it. So by the description here of toric Mori fiber space, actually six of them. So for toric surface, I drew this picture. So in that case, D is 2. So we have 3 rays. We have 3 rays. And this one actually present P1. And this is the ray of A1, and also lattice fan of A1. So this is the projection. This is the projection. And V3 is a primitive element. So that means A and B are relatively are coprime. So we can assume, for example, A less than B, for example. So by the theorem before, which means B is the multiplicity of the original, of the central fiber. Okay, so how can we prove for the third case? Suppose X is epsilon LC. We want to show B cannot be too large. The multiplicity cannot be too large. The basic idea is, for example, if we have epsilon is a positive real number, we just take some, how to say this, some some shape with 4 edge generated by, for example, epsilon V1, epsilon V3, epsilon V2, and a negative epsilon V3. So this is a central symmetric graph. And it's easy to calculate the area. The area of this this graph is this epsilon squared over 2b. Okay, so by Minkowski theorem, if B is large enough, then there would exist some integral points inside this graph, but this would contradict to X is epsilon LC by the computation of singularities of toric varieties. Yes, this is basically the idea. So the area of this is epsilon squared over 2b. If b is large enough, very large, then this graph will exist some integral point. Then this shows this surface is not epsilon LC. So b has to be bounded by something. So this is just some baby example to illustrate. And also I think this can give a lot of examples. If B is very large, then the multiplicity of central fiber can be very large by the descriptions before. Okay. All right. Okay, so then let's turn to the proof of this Mann theorem. Not Mann theorem, the proof of this first. The proof of first this case, special case. Let's proof of this case, about for multiplicities, and then we turn to the proof of Mann theorem. Okay, so we need to use a trick. We call it isogeny. Actually, not I call it as Shokurov call it isogeny. It also used in my thesis. This is simple. For example, if n prime is a sublattice of finite index in n prime and n are two lattices. If epsilon to be a fan in this n tensor R and n prime tensor R. So because this is a sublattice of finite index, so they have this tensor R are the same linear spaces. Then we denote this group. This group is a finite group by n quotient n prime. Then the toric morphism induced by x prime n prime sigma to x n sigma. So it's nothing but this corresponding to X is a quotient, X prime, quotient G. So this is just X prime to X prime quotient G. So this is the fact. So which means we know that every toric variety is given by lattice and fan. So this theorem says if we fix the fan the same, but lattice change, lattice n prime is a sublattice, then this toric morphism is nothing but X prime to X prime quotient, this G. G is the finite group. Is n quotient n prime. So this is a trick. For example, let me illustrate with a simple example. So suppose the cone is given by this is generated by E2 and 2E1 minus E2. Then dual cone is this, and the shape just this is a cone. Yeah, I think the geometric graph. So we see from here, this cone is not, this element is not primitive, which means the generator of this is not a basis of the whole lattice. So if we take the sublattice generated by this and this, then this toric variety is isomorphic to C2. So which means if we still take this picture, and the fan is like this, but the lattice I use is generated by this one and this one, then we would have a sublattice to this. Then this would corresponding to C2 to C2 quotient Z2. It's nothing but this one. This is the what we want to say. All right. Now we come back. So first we need to do some reduction. The first reduction is before, as we said before, the general fiber is a toric Fano varieties of Picard number 1. We first want to reduce it to P, to projective space. So how can we reduce? We use this trick of isogeny. So first we can assume general fiber is P at D minus 1, and the degree is bounded. I will explain. So this is our original F, X to A1, and the general fiber is toric Fano of Picard number 1, possibly singular. But we can take a sublattice such that it is nothing but P projective space. So actually X prime here, we just take that isogeny. Okay. And another fact we need is by Borisov's brother, and in general BAB's theorem, BABB theorem. So epsilon LC toric Fano varieties of Picard number 1 form a bounded family. This is Borisov's result. Maybe their thesis of undergraduates or something. Yeah. Okay. So in this case, what is such in toric case, such family form a bounded family means the fan of such epsilon, the general fiber, can take only finitely many possibilities up to an action of GLD minus 1Z. So we can take only finitely many possibilities. So this make this degree pi bounded. Degree pi is given by the quotient of the lattice. So this has finitely many possibilities, which means this degree is bounded. This is important for us because degree is bounded, then we can reduce to this case, general fiber is this. If we can prove this, the multiplicity is bounded, and plus the degree pi is bounded, then we can say the degree of this is bounded. Okay, so here we need the result. And the second trick is like this. So as we mentioned in the classification of Toric-Mori fiber space, this U is A1 minus 0, which means C star. So F pullback C star is a trivial product, PD minus 1 times U. Then we can assume D is greater or equal to 3. Otherwise, when D is 2, that's just a surface, for surface case. Surface case, we already proved either by combinatoric information or Bika's result. So here we can assume D greater or equal to 3, which means general fiber are at least surface or dimension greater or equal to 2. Then we want to choose a toric invariant point P in this fiber F, and take a closure. So we know that every fiber has a toric invariant P, and P cross U. U is actually a line, which is a line here, and then we take a closure. We do blowing up. So we blow up this pi of this X. So X is at least dimension 3, and this is actually a line, and we blow up, we get Y to X to A1. And X to A1 is relative pK number 1, and this is relative pK number 1. So we have this relative pK number 2. So the reason for doing this, we try to do induction of dimensions. So for example, if we have P2, for example, D equals 2, P2 blowing up 1 point, then we have 2 extremal rays. One is corresponding to this blowing up. The other is corresponding to this P1 bundle structure. So here is a idea. So one is corresponding to this blowing up. The other thing, we want to try to get some P1 bundle structure here. So we need to run a suitable MMP, and Y to Y prime here is possibly some flip and flow flips. Then Y prime to W is a relative dimension 1 case, is corresponding to P1 bundle structure. And then we get this Y prime to W to Z, and we know from here we can use Bierka's result, and this singularity will not worse than Y and as same as X, and Y prime to W the singularities can be worse but still under control by Shokurov's theorem or in relative dimension 1 case. And from here to here we can use induction because the dimension is dimension drops. So this is a main idea. Okay. All right, this is a main idea. Now we assume actually I already explained. Okay. Now I come to the main theorem which says if D is a natural number and epsilon is a positive real number, then we claim there exists some alpha and delta, some real positive real numbers depending only on D and epsilon satisfy the following. And if we assume X delta is a pair, and delta here denotes the toric invariant divisor, and we consider our toric contraction from X to Z, and we assume XB plus M is a generalized epsilon LC pair. So generalized pair actually was introduced by Bierka and Professor Toric Zhang, and M is some NAF divisor push forward, and B just some pair, and then we can similarly define the minimum log discrepancies and define their singularities. And M prime is just NAF part, and M is the push forward of M prime. And suppose Kx plus B plus M is trivial over Z, then let this gamma alpha to be the average alpha B plus 1 minus alpha delta, and n alpha just alpha times m. Then we can again apply adjunction, kx plus this adjunction. The conclusion is z gamma alpha z plus nz alpha is generalized delta LC. So once we have this main theorem, for example, if this is delta LC, which means, as we explained before, the all birational model of these coefficients are less or equal to 1 minus some delta, which means the coefficients cannot be too small. So which means the multiplicity cannot be too large. And we can also from here to deduce Alexeyev and Borisov's results. If this is generalized delta LC, then you can get this is delta LC. Okay, the proof actually similar. Just recall. So before, in that case, we prove a very special case for multiplicities. We prove for x to a1. But in general, x to z, if we consider toric Mori fiber space, which is similarly, but of course, proof will be more complicated. So we assume f from x to z is a toric Mori fiber space. Then first, again, use isogeny. Isogeny, because we know at this time general fiber is a Picard number 1 Fano, toric, possibly singular. We use this isogeny. We can assume that general fiber of F is P. P is projective space, P to dimension x minus z. And we denote x tilde to x to be pi. This is a finite morphism. And again, because x is epsilon LC, so general fiber is epsilon LC. And again, by Borisov's brothers' results, we know degree of this pi is bounded. And we can rewrite the formula like this: pull back the general fiber, pull back generalized pair. We have this. But here, one thing to note: this B tilde might be negative, which means X tilde and B tilde might be a subpair, so the coefficients can be negative. So this is one reason we need to do this average to make it to be effective, and then we can run MMP. All right. So we get this and use the same trick before, which means again, we need to first assume dimension of x is greater, or relative dimension of this is greater or equal to 2. Then you can choose some point z on each fiber and p. Some point on each fiber p times u. Then you take closure. I mean, it's, again, use this trick. The purpose, we want to get two directions contraction. One is divisorial, the other is P1 fibration. Okay. So similar trick before, we want to use that again to blowing up something and get a P1 bundle. Then we can buy induction. So this is basically the idea to prove if X to Z is a toric Mori fiber space. For general case in our main theorem, we consider X to Z is a toric contraction. Then we need to run an MMP on Kx by BCHM. This can always terminate. So we get some Mori fiber space X to V to Z, the relative. So if V to Z is birational, then we see that the singularity of these are the same. So we can replace Z by V and apply toric Mori fiber space here. However, in another case, if dimension V is greater than Z, then this part is another toric contraction. We need to apply induction on dimensions. So I think this is basically outline of the proof. The important idea I already explained, and also I introduced some examples. So I think I will stop here. And thank you very much.
All right, thank you. So any questions? No questions? Okay, then let's thank speaker again. Thank you, Yifei. All right, so let's
Thanks.
move to the next. Well, I don't see the speakers and the no host.
I think we're a bit earlier.
Yeah.
Yes. I stopped.